Alright, welcome to another science lesson, one-on-one. And so here, me and Mr. An, we're working on understanding the stars, which is grade 9 science things. Cosmic radio wave background radiation, Hubble's redshift, and then the ratio of hydrogen to helium. Okay, let's just read it now, shall we?
Okay.
Start out very hard, but the core is expanded. And the theory is correct. Can you read that?
The Big Bang Theory predicts that the universe started out very hot, but cool as it expanded. If the theory is correct, scientists predict that the temperature of the universe today should be less than 10K of Kelvin, or minus 263 degrees Celsius. Kelvin is a unit of temperature similar to that degree of Celsius. In that one, Kelvin is equal to 1 degree Celsius. However, they are not the same term of absolute zero. 0 degrees Celsius is equal to 273 K. To measure the temperature of the universe, you can use light, which is a type of electromagnetic radiation. Other examples of electromagnetic radiation include visible light, radio wave, and X-ray. The type of light given off by an object can tell you its temperature. In 1964, two American scientists working with a telescope that detected radio wave accidentally discovered cosmic microwave background radiation that came from deep space. It could be detected in the background, that is, in any direction they point their telescope in. The analysis of this radiation showed that space was really cold, around 3K or minus 270 degrees Celsius. Exactly
as really cold out there, except from when you are near to the sun or any bright stars, But otherwise, it's just really cold out there.
Yeah. Ratio of hydrogen to helium. According to the Big Bang Theory, the first element was hydrogen. Other elements such as helium were derived from hydrogen at a periodic table rate. The Big Bang Theory predicts a 3-to-1 mass ratio of hydrogen to helium. This is the ratio that you would expect to find in deep space.
3-to-1 mass ratio of helium. So basically, for every hydrogen, there should be 1 helium in space.
Yeah.
Which is basically, we use a Hubble telescope and we check it out. We can analyze composition of elements of gas clouds in deep space. Because basically gas cloud, they emit some kind of rays as well, and we can analyze that, and so we can figure out what is their chemical composition, like what they are. So we can basically figure out that the proportion is the same, like 3 hydrogen to 1 helium. This gas cloud is massive.
Yeah.
Gas cloud on the in space is massive. It's just so big. It covers like, you know, even the entire solar system, even more than that. It's really big.
It's kind of. This is the ratio that you would expect to find in deep space if the Big Bang occurred about 13.8 billion years ago. Using new telescopes that orbit the Earth, such as the Hubble and Kepler Space Telescope, astronomers can analyze the composition of elements in gas cloud in deep space. They have discovered that the proportion of helium to hydrogen is the same as what was predicted by the Big Bang Theory. Modeling the expanding universe. Activity, the following activity, simulation of the expanding universe. Draw a four-dot with a marker or pen on the surface of an inflated balloon and label them A, B, C, and D.
These dots represent stars. So as the balloon expands, you will see that the dots just gets further and further from each other, right?
Yeah. Inflate the balloon slightly so it's less than half full, and temporarily seal it close. Use a clip, tape, or elastic band. Measure the distance between dot A and the other three dots, and record your measurement in the row labeled low in a table like the one shown. Inflate the balloon some more until it's about half full, and then reseal it. Measure the distance between dot A and the other dot, three dots, and record your measurement in the row labeled medium. Inflate the balloon some more so that it's almost full. Be careful not to burst it. Seal the balloon. Measure the distance between dot A and three dots and record your measurement in the row labeled full. So it's like when it's like low, it's just like very close to each other. The medium, it's like spread out a bit, and just like full, it's just like spreading very far from each other. So what happened to the parent dot as the balloon was inflated? Data provided. How is the balloon a good model for the expanded universe?
Good enough.
Okay. Okay. Galaxy.
Galaxies. Just a lot of stars, like trillion, millions of stars groups together. They held together by gravity, so basically they attract each other, or basically there's something that attracts them. It's called gravity.
Yeah. Galaxies are a large group of stars held together by gravity. There are billions or even trillions of stars in a galaxy. We live in a galaxy called the Milky Way. It contains most of the stars and constellations you can see in the sky. It is estimated that there are more than 400 billion stars in the Milky Way. You can see a profile side view of the Milky Way on clear night sky.
Never
Clear
seen
night
that
if you
before. Basically, the sky is always polluted with light. I mean, in the city.
yeah.
Always. So it's very tough to see something like this. But when you are in, let's say, a countryside, or on top of a mountain, for example, you can see it.
Or somewhere like not very crowded.
Say again?
Somewhere it's like not very crowded
Mm-hmm.
or like that. So it's like hard to see like those stars up in the sky.
True.
It's like very rare.
Mm-hmm.
Other galaxies are a great distance from Earth. They can be seen only with a telescope. Edwin Hubble was the first to observe galaxies beyond the Milky Way. Galaxies come in several shapes. Hubble developed a way to classify galaxies based on their shape. There are six main types. Press on each
It depends
to
on their shapes. They are classified into like these 6 main types,
oh
Spiral, like a spiral,
yeah. Spiral arm relic.
It's on a central bulge containing billions of stars.
The bulge is circular in shape. Elliptical. Is that how it's called?
Oval shape. They have the shape of oval, similar to a football or rugby ball, but they do not have any arms. So basically, it's like you cannot see any arm. It's just like a plate, It looks like a plate.
Irregular. These galaxies have no defined shape and no clear spiral arm. They look like blob or clouds.
It's just basically irregular shape. They're just like unknown shape. You don't know exactly what their shape looks like. No clear spiral arm, no clear structure, just like blobs or clouds,
And lenticular. Lenticular galaxy has
Lenticular.
probably
Both elliptical and spiral galaxy. So they have both an arm and that shape. It looks like oval, I think, or elliptical. linear central bulge, and no spiral arm. Oh, they say no spiral arm. So right in the middle, there's like a line, you know. Central bulge is like a line in the middle, and there's no spiral arm. But there is still a huge chunk of something.
Ring. This is the ring-shaped galaxy,
Much of which is empty space.
Barrow spiral. These galaxies have arms that radiate from a bar-shaped
galactic bulge.
The Milky Way is an example of a
bar spiral.
barrow spiral.
So it's like there's a bar, and then there's a bar spiral. Look like a crowbar, you know, like a crowbar. You know what a crowbar is?
Yeah, crowbar.
Okay, look like a crowbar, like in Half-Life crowbar, you know. Barred spiral. Bar-shaped galactic bulge. So we have a barred spiral shape.
Star. Galaxies are made of stars, and stars provide light and energy to drive most processes
in the universe.
The sun is a star, and the light
and heat it provides allow life to exist on Earth.
So what is known about stars from observing them
through telescopes, of course. You know, that's the only way, because there's no way we can reach them yet with our current technology now. So we can only observe them. We humans are still quite primitive, to be honest, when it comes to space technology. We are not that advanced. That's a problem. So we can only observe now. We haven't been able to travel.
Types of star. Star have four main types of composition: supergiant, red giant, dwarf, sunlight star. Some of these are visible in the photo. Supergiant are hundreds of times the mass of the sun and are very bright, usually bright blue. Red giant are slightly bigger than the sun, glow a bright red. Red giant have solar mass of 10 to 100. Sun-like stars have masses similar to the sun, in the range of 0.5 to 10 solar masses. Supergiant, red giant, and sunlight star are visible in this image. Dwarf stars are also present, but are too small to see. Dwarf stars are sun-like stars that have collapsed into a small, dense ball of gas.
dwarf. There's a reason why they call it dwarf stars, because basically they're just smaller than a real star, and they're just too dense. So when the thing condenses together, the star becomes smaller. Small, dense ball of gas, 100 times smaller than the sun in diameter, but relatively heavy. So they just condense together, you know.
Yeah.
It also depends on which stage of their life cycle they are at. So when a star like our sun burns out energy, like let's say in the next 5 billion years or for 10 billion years more, it will become like, it will condense. It will become a red giant, because it will get bigger, and then slowly the material will just basically get condensed into our dwarf star. That's what people predict. Just prediction, you know. Things can change.
Brightness. The brightness of a star is called luminosity. This is a measure of how much energy the star gives off in a period of time, giving time period, usually 1 second. The luminosity of a star is often reported in relation to the sun because we are most familiar with the brightness of the sun. Some stars are more luminous than the sun, while others are less too so. The brightest star in this picture from the Hubble Space Telescope are thousands of times brighter than the sun. Stars appear to have different level of degree or brightness or luminosity. The brightness of a star is related to two factors: its
How
size
bright they
and
are.
its distance.
Size and
And its
distance from
distance.
Earth. Of course, the bigger it is, of course, the more light it emits, right? And how far
Yeah,
it is away from Earth. If two stars the same size, the closer one will appear brighter, of course. Like, for example, if you have a light in front of you and then you have a light like 10 meters away from you, of course, you will see it differently, right? You will see the light, the brightness differently, depending on the distance between it and you.
colors.
Mm-hmm.
Although star appears white and as though they are twinkling, when you look at them with the naked eye, a telescope reveals that they come in a variety of colors. The colors are related to the star temperature. Stars typically come in one with 5 colors, ranging from coolest to hottest:
Mm-hmm.
red, orange, yellow, white, and blue. The sun is a yellow star.
Of course, you need to know this one as well. Like the color of the star are related to its temperature. So the white one are the hottest, and then the blue one are the second hottest. So sorry, blue is the hottest, sorry, and the white is the second hottest. But then the one that's red, basically it burns at around only like 300 to 400 degrees Celsius, to be honest. But yellow, it's about say 5,000 degree on its surface or something like that.
That's a lot.
You know about the flame of the stove, right? Gas stove.
Yeah,
So when we turn it on, it becomes blue light, but when the temperature drops down, it becomes yellow light, isn't it?
Yeah.
Same thing applies. So basically the same thing applies to stars. So yellow, it means that it's just only medium temperature, and the sun is a yellow star. Blue, oh my god, it's just so hot. The hottest.
Um, Size. A star's size is measured in relation to the size of the sun. In units called solar masses. The mass of the sun is set to a solar mass of 1.
Mm-hmm.
A large star may have a solar mass of 300 or more. A small star has a mass that is a fraction of 1. Composition.
Sorry.
Composition refer to the oh, composition refer to the element a star contains.
Mm-hmm.
For example, two elements that most stars contain are hydrogen and helium.
Yes.
Size of star are measured by a unit known as solar mass. The brightness of a star is determined by two factors: size and shape. Star comes in four colors: red, orange, white, and blue.
Mm-hmm.
Supergiants are very large, bright star. That's true. Distant to star. Compared to distant to Earth, distant in space are so large. Unit measurements such as kilometers.
No, we don't use kilometer anymore because basically in outer space, it's just so large. Kilometer is nothing now. We measure them with light year, you know. So basically, it's just how the distance that light travel in a year is massive. It's a lot, but we measure it with light years, you know, to see how big space is. It's so big that we have to measure with a new unit now, light year. Mm-hmm.
To simplify this, astronomer measure the distance to star using a unit called light year. Despite its name, light year is a measure of distance, not time. It is the distance that light travels in 1 year. To know how far light travels in a year, you need you need to know how fast light travels, or the speed of light, which is 300,000 kilometers per second, or 3 times 10 to the power 5 kilometers per second. 3 times 10 to the power 5 kilometers per second. 3 times 10 to the power 5 kilometers per second, or 3 times 10 to the power 5 kilometers per second, or 3 times 10 to the power 5 kilometers per second, or 3 times 10 to the power 5 kilometers per second, or 3 times 10 to the power 5 kilometers per second, or 3 times 10 to the power 5 kilometers per second, or 3 times 10 to the power 5 kilometers per second, or 3 times 10 to the power 5 kilometers per second, or 3 times 10 to the power 5 kilometers per second, or 3 times 10 to the power 5 kilometers per second, or 3 times 10 to the power 5 kilometers per second, or 3 times 10 to the power 5 kilometers per second, or 3 times 10 to the power 5 kilometers per second, or 3 times 10 to the power 5 kilometers per second, or 3 times 10 This is so fast that it takes light only about 1 second to travel from the Earth to the Moon. Little over 8 minutes for light travel from the Sun to Earth, a distance of more than 150 million kilometers. Takes in scientific notation, the distance of one light year is 9.4608 times 10 to the power of 12 kilometer. You can see why astronomers prefer to work in the larger and therefore simpler unit of light years, rather than in tiny kilometer, for example. The North Star Polaris is 4.434 light years from Earth,
Mhm.
which is much easier to work than 4.11 times 10 to the power of 15.
We
That's a
don't want to
lot.
have like long numbers with like huge yeah, zero, a lot of zeros, right?
Yeah. Birth of star. Stars are made from dense clouds of hydrogen and helium gases, created using the birth of the universe. These gases that collect in large swirling clouds mixed with dust are called nebulae.
Nebulae.
Nebulae, yeah. Nebulae.
Nebula is like singular and plural form of that. One of some of the most beautiful objects in the universe, because basically they looks colorful and it looks just like, you know, heaven. So that's why we say it's some of the most beautiful objects in the universe. Omega Nebula. Mhm.
Example, the Omega Nebula is the birthplace of billions of stars.
Mhm.
Gravity sometimes causes part of a
Nebula
nebula
gas cloud
gas
condense. Uh-huh.
into a much denser spinning whirlpool of
Whirlpool
gas.
of gas and dust. So it become like a plate, you know.
Yeah. following picture illustrates the birth of a star. Gravity caused the gas in the nebulas to swirl and condense, forming a
Forming a
dense
dense
center.
center, but eventually become a star. Basically, they just get denser, denser, and denser, and denser until, like, a star is born.
Yeah.
It's not just the name of a song. Basically, A Star is Born is real. I mean, it can be just condense, denser, denser, become like a star finally.
The life of star. All stars produce enormous amount of energy through a process called nuclear fusion. Nuclear fusion is the fusing together of two nuclei to form one. It takes immense amount of heat and pressure to push two atoms close enough together to fuse them into one.
Mm-hmm.
Stars are formed by gravity pulling huge clouds of hydrogen, gas, and dust together into a dense sphere. As the star takes in more gas, the force of gravity increases, squeezing the hydrogen atom in the core even closer together. This creates condition ripe for nuclear fusion. Two individual atoms of hydrogen combine to form one atom of helium, and tremendous amount of energy. Remember, hydrogen has one electron in its outer shell, so if the nuclei of two fuse together, they create a helium atom. The nuclear fusion process stops, and the star begins to die. When it's run out of hydrogen atom,
When you run out of
the atom
energy,
will be
basically slowly, just when you slowly run out of hydrogen atoms, then helium will be produced. I remember, yeah. The death of stars.
All stars are born, live,
2 million, a billion years. That's a lot, and then they die.
longer than us.
How long a star lives and how it dies depends on the initial size. Like how much materials condensed to become a star at first. That is its initial size. And of course, it affects like how the star will live, how long it will live too.
Low mass stars begin their life as dwarf stars.
Star.
Dwarf stars may produce small amounts of light for
Approximately
approximately
100
100
million
billion
years.
years. These stars live a very long time. They eventually grow cold and dark.
At which point it starts known as a black dwarf.
It's just like black hole.
No, not yet. Just black dwarf. To become black holes, you have to be extremely dense. So basically, not now. Black dwarf are not black holes. They're not enough. Well, black. Okay. Medium-sized star, massive star. Let's see now. Of course, it depends on the mass of the star. Then we will know if they will become black holes later or not. So our sun will not become a black hole. According to what scientists speculate, but we never know.
Medium-sized stars, such as the Sun, have a lifespan of about 10 billion years. The Sun is estimated to be about 5 billion years old.
It's halfway through its
So
life
it,
already.
So it is halfway through its life. In a few billion years, the sun will expand to become a red giant. It will get so large that
engulf the Earth.
before running out of gas,
It's just like boom, it's just getting bigger and will consume all the 4 inner planets, you know, that's what the people think. So Mercury, Venus, Earth and the Mars will be consumed in that big giant. So, and then slowly they eventually collapse, so the whole thing just shrink down and become a black dwarf. I mean, we should be able to have much better technology than now to colonize other planets already. You know, by then it's like 5 million years, 5 billion years a lot. It's a lot. Okay, let's just continue now reading it. My body is still aching from the effect of like the vaccine, the 3rd jab. It's Pfizer shot. Have you got your 3rd one? Hello? And still there?
black holes.
Okay, black holes now. Sometime when a supergiant star explodes into a huge supernova.
Instead of the material spreading out into space, it'll collapse back in on itself. The large mass of the supergiant star is now packed into a tiny volume. This large mass exerts so much gravity, black holes form and cool in everything around them, including star, galaxy, and even light. They are called black holes because no light can escape them, so they are invisible. Even though black holes can't be seen, we can detect their existence by observing the behavior of nearby matter as it flown into the center of the hole. Wonder of the universe. You have learned a simple version of what happened to a sunlight star during its lifetime. There are some other details of the star life cycle. To learn about these details, watch the short video Star, Death, and Creation of Element from the BBC document series Wonder of the Universe.
So it's balanced each other out. You know,
Yeah.
gravity is inside getting in. But that pressure when the thing created, the elements are created, it's just pushed outward. So the two forces are like the opposite of each other. Like that. Self. So basically when you don't have any helium anymore, there's no force outward anymore. So gravity will eventually push everything into the center, you know. You can continue.
The temperature rises once more, launching stage 3.
It just falls like that.
Take a break for a bit.
Okay, sure. Okay, so what we have here, the sun. Okay, the nearest star to the Earth is the sun.
It keep the temperature high enough for water to remain in liquid form
Most of the time.
Plants use light for photosynthesis, a process that converts
Photon in
energy.
light, synthesis is to produce something.
Yeah.
So photosynthesis means a process to produce things with the effect of sunlight.
Process convert that a process that convert the energy from sunlight into chemical energy. Plants use this energy to grow and reproduce. The animal eat the plant to get the energy they need to live. The entire network of life on Earth ultimately depends on the sun energy. The sun is not a solid object. It's a huge ball of incredibly hot condensed plasma with instant layer.
So there are many layers in the sun, basically just like a very hot object. Plasma. Basically plasma is the fourth state of matter. So you know solid, liquid, and gas are the three states of matter that we know. But plasma it behaves just like liquid, but it's not liquid. Plasma is produced when it's like very high temperature.
Because its temperature is so high compared to the Earth, we use a different temperature. Degree, Kelvin, 0 degree Kelvin, written as 0K without a degree symbol. It's about negative 273 degrees Celsius. Core. Description. In the most region of the sun, very dense and very hot at almost 60 million K. Function. Generate heat by nuclear fusion. 2. Radiated zone. Layer around the core not as hot or as dense. Function. Transfer energy outward from the core by radiating heat. Convected zone. Layer where hot gases rise from the radiated zone. Function. Convention. Transfer heat energy outward by circulating current. Or photosphere. The outer visible layer of the sun, also called the sun surface. Temperature is relatively cool at 6000 K. Function. Convert heat energy into light energy. Chromosphere. Position. First layer of the sun atmosphere. Temperature increase as you move further up, reaching up to 1
million
K.
Kelvin is like million degrees Celsius, like a lot. The sun is basically a massive nuclear reactor, you know. Very, very, very hot in there.
Ooh.
The sun is basically a massive nuclear reactor. It is. Every star is a massive nuclear reactor, because in there they changes the element to become new elements, right? So that is what nuclear reactors are about, and it produces a lot of energy. All stars are just like nuclear reactors, massive ones.
Six. Corona. The outmost layer of the sun atmosphere has volume equal to the rest of the sun. Function. Create solar wind which extend into space. Solar flare. Large spark of gas and energy that form in the corona and release dangerous
X-rays into space.
function. Particle from solar flare cause aurora, northern and southern light, visible near the poles.
So auroras basically just like it just basically it's like from the surface of the sun. It's these kind of waves just emits out like and then go back. These are called auroras. Only at northern and southern lights of the sun. Of course, solar flares are dangerous. They release dangerous X-ray into space. X-ray is very penetrating. So basically, they penetrate everything. That's why we can see our bones when you do X-ray, you know. But then X-ray is actually quite dangerous. So when we travel to the outer space, it's actually quite dangerous because we are not protected by our atmosphere anymore. When the ozone layer it's getting damaged, same thing happens. These dangerous rays can get into the earth, can get to the earth's surfaces very quickly, and we have skin cancer and things like that, you know, that we're exposed to too long. Not something fancy.
Yeah. Study card. To prepare for many tests, and student finals.
Prepare for tests when you still find helpful to prepare study cards, organize important concepts and ideas. This is just like for study cards, you know.
Yeah.
Fold, take study cards out. Remember key ideas about concepts. Well, knowing how to make study card actually helps because you don't have to bring the whole book. You just need cards, and then you can just okay, what's that? Okay, what's that? And you can learn concepts easier that way.
Solar flare.
Consolidation.
Study card to summarize your learning. Grade 2 or 3 study card on concept you have learned
Yeah,
really
this is support these learning goals. Keep the study card without a stick card onto the flip. They have already created. Like, you know, cards should be like hard paper, because otherwise you will ruin this paper if you touch it so many times, you know. Should be hard paper. I created a lot of study card when I was younger. Wow, but then it just only for exams, and then finally just throw it away. Well, but it does help. It does help.
That's it to 3.2, studying understanding stars. Hold on.
Mm-hmm.
Share screen.
Okay, the solar system. Now we're moving to on solar system now. Okay, modeling the solar system. Sorry, I'm just like too tired because of the jab, the vaccine. It's feeling crazy. Wait, is it? Moment. Just a moment, please. Oh, today is a new period of tuition fee, so you should ask mom. You know, today is start a new period of tuition fee paying, you know. You should tell mom. Okay, your microphone, please. You should tell mom, okay? Should remind her to pay the tuition fee.
Okay.
Because today is a new one already.
The solar system.
Mm-hmm.
This discovery of the structure of the solar system and its origin are some of the biggest discoveries in science. In this learning activity, you will learn how these discoveries came about and what they tell about us about the potential for life on other planets. You will also take a tour of the solar system, learning about the 8 planets and the objects orbiting the sun, including asteroids and comets. Final part of the activity focus on the Moon, Earth's only natural satellite. It is naturally visible in the night sky and look different depending on its phase. An atom, our solar system.
Mhm.
Model of solar system. Location, the star and planets are constantly moving if you look carefully at the night sky over a long period of time. You can see what this looks like. Here's a photograph that captured the motion of the star at stake in the night sky. The location of a celestial object in the sky depends on when you look. About one thing is clear: it seems as if Earth is standing still and everything else is moving around it. Early astronomers noticed this too. They create a model of how celestial objects, such as planets and stars, move in
Mhm.
relation to the Earth. In most cases, the model had the Earth at the center of the solar system, with everything
Everything rotating
rotating.
around it.
This is known as geocentric or Earth-centered model of the solar system. Implementing geometric model. But
Plotemy geocentric model. So basically, there were several models of how the solar system looks like in the past. So we have geo, which means Earth. Centric means it's the center. So geocentric models say that the Earth is the center of the universe. So that's what people thought, because you see that all the stars and the sun and the moon just move around us, right?
yeah,
So it's easy for people to basically think of a model that is called geocentric model. Just read the story, you will see that there are other models as well.
Claudius Clemente was a Greek astronomer who lived in Egypt about 2000 years ago. He developed a geometric model of the solar system. In Clemente model, all of the all of the known planets, as well as the Moon and the Sun, orbit the Earth in circular orbits. To account the time when the planets appear to reverse their direction of travel, called retrograde motion.
Mhm. You know what
Mr. Jack,
retrograde, right? Retrograde means like they go backward. Instead of going forward, they just go backward. That's called retrograde motion, going backward.
Mhm.
In astrology, when things go retrograde, there are a lot of when things go retrograde, a lot of things can happen, in astrology, but that's later. When you see the thing on the sky just go backward, the thing represented by them actually go backward as well. Like for example, Mercury, the planet Mercury. It's representative of communication, business, the mind, how we think, and our mouth, how we communicate. So when you see the Mercury go retrograde on the sky, you will find it more difficult to study, find it more difficult to make decision, and you will make mistakes more often. Things will go slower, the internet will go much slower too, and you might end up having accidents, car accident or something like that more. Things just slow down, doesn't go well. Business doesn't go well when it's like Mercury retrograde, which is like about 3 weeks. So every year there are 3 times when you see Mercury retrograde. Every time it's like 3 weeks. Those 3 weeks, those 9 weeks, I mean, totally, are not the time when you should sign contract, not the time when you should do something big, you know, because things just like goes really slow. I mean, that's astrology, but for astronomy, it just means nothing beside from it goes backward, you know.
Yeah.
All right.
According to Lamy theory, the stars are fixed onto a rotating celestial sphere that surround the planet. Like the planet, the celestial sphere also rotate around the Earth, which explain why the constellations move across the sky over time.
Mm-hmm. So if according to this model, the moon never goes retrograde, it's just because basically it's real, the moon moves around the Earth because it never goes retrograde.
Yeah.
But the other planets, you always see them going like backward. So something must have gone wrong, right?
Yeah.
Something must have been weird. So something was wrong with this geocentric model. So that's why other scientists have been trying to think of other models. Slowly, you will see more type of models, and with historical connotations to go with it. Like, according to history, there's a guy named Copernicus. You know Copernicus? Kopechnik.
Yeah.
He was the one who proposed the heliocentric, helio means the sun, heliocentric model, which means the sun is the center. And so a lot of people back then, they just don't like changes, they don't like new things. So basically when they hear that new model, they thought it was like some kind of witchery, it was a demon idea or something like that. And so they didn't like Copernicus at all. Galileo, like about 50 or 60 years afterward, I mean, he realized that Copernicus' idea was correct. But then he tried to protect that idea, but then the church actually hated him so much. They tried to prosecute him because they thought it was kind of witchery, you know. And as a result, Galileo was burned alive.
Whoa.
He was burned alive because he was following that that heliocentric model. But that was like maybe 400 years ago, when humans are still very how can I say, not so smart. How to say?
They believed everything.
Well, whenever the new things, people will be like, they resist changes, you know, people are always like that. People resist changes. Just think about your family members either. You don't like to change, do you? You don't like to change it for your school. You don't like to change your country of the resident that much. You want change, but you don't want to change yourself. You like to see the changes, the good changes, but you don't want to change yourself. That's human. Sometimes they can act in a radical way, just like burning someone alive, like Galileo, you know. So that's what I'm saying. Now, let's focus on this one.
Elementary geometry, it could explain and predict the regular rising and setting of the sun and the moon. It was less able to predict the exact motion of the planet even with the additional of a small rotation that each planet makes within the orbit. Nevertheless, it was good enough at forecasting most celestial events, including eclipse, to have widespread support. Elementary geometric model was accepted for the next 1,500 years. Which opposition could
The Ptolemy geocentric models explain, and which could it not? What do you think? After you have read this, I'm gonna try to stand up now. I'm getting so fat by sitting too much. I'm too weak too. And then next you have Kopechnik's heliocentric model. Alright, so it could not explain why planets just go backward, like retrograde, right?
Yeah.
So that's what it could not explain. But it could explain, it could basically predict like when the eclipses will happen. You know, eclipses are like when three objects on the sky like in arranged in a line, you know. Like solar eclipse, lunar eclipse. When the sun, the earth, and the moon are in the line, you know, that's when we have eclipses. It could explain. It could basically predict these.
Yeah. Observation. Why? Why do you think this model is widely accepted even though it cannot explain all observation?
Copernicus heliocentric model. Because basically eclipses are important, and if it can explain that, then that's more than people wish for. But when things are going backward like that, retrograde, it's not that much important to human understanding back then. That's why people still accept geocentric model, you know. That's what I think. But maybe suggested answer may say otherwise. There were no better explanation at the time, exactly. Because back then people didn't know much, you know. If there's something available, they will accept it, okay? Yeah, you know. They will gladly accept it. Okay, Copernicus heliocentric model. Okay, so about like 1500 something, Copernicus arrived at that the sun is a center. Yes. And until now, we're still using this model, and it's still proven true. It could explain a lot of things like retrogrades and things like that. Because if you think about it like this, if you're here and there's a planet there, and so basically that planet will have to move around the sun, right? That planet will have to move around the sun. So sometimes you see it going, sometimes you see it going like this way. But then another time it will go backward like that, right? So it go back, and then it go, and then it go this way again, and then when it goes around the sun, it just go backward again, right? So that's explain, like, you know, how planet go retrograde, because basically they don't rotate around the Earth, they rotate around the sun. So from the point of view of the Earth, we see it only that way. Can you turn on your microphone, please? Okay, next time, please share like the whole thing. I mean, all the tabs, not just this one, okay?
Oh, yeah, sorry.
Okay, please.
Envision the sun and planet in the same plane and believe the planet traveled in circular orbit around the sun. This was known as the heliocentric sun-centric model of the solar system. Copernicus published his model in 1542. This model was further legitimized by other scientists over time. Galileo, for example, made some discovery about the phase of Venus that support for his model. Another astronomer
Kepler. Johannes Kepler of Germany between the orbits of the planets were elliptical rather than a circular. So basically, it's not like like in a circle, but basically it just go like oval shape, you know, like oval shape. Or elliptical. So sometimes the Earth is nearer to the Sun, and sometimes it's further from the Sun, because of this oval shape thing, you know. And that explains like some time of the year is like hotter than the other time of the year, you know.
There was some resistance to accepting the heliocentric model for a couple of reasons. Change is often difficult for people to accept, and
there you go. Nobody accepts changes. That's why people died. Life is just tough.
Earlier you saw how Trump's support for the heliocentric model led to his conviction for heresy by the Catholic Church in Rome and the sentence of house arrest for the rest of life. Right. His life as well.
House arrest for the rest of his life.
That's
so basically, he's not allowed to go out. He's not. Everything he wrote will be censored by the church. You know, heresy. So it's like a witchery, heresy, witchery, and it's bad for human. So that's why, I mean, I remember that he will burn alive by the church even. But I think this site, I mean, they didn't mention that. Because it sounds sounds very brutal if you mention that, you know, in a book, in a website like this, educational website.
Despite the resistance, evidence support of the heliocentric model grew quickly. For example, using Newton's ideas about gravity and Kepler's ideas of oval orbit, astronomers were able to predict the location of a new planet, Neptune, over the years. More than the
More astronomical discoveries support this heliocentric model. So basically, throughout the years, there are more and more evidence that prove that, okay, heliocentric model is the one, it's the real one, it's the true one. So we only found Neptune around, I think, 1870, around that 1870. And then later we found about Pluto at about 1930. Based on Newton's idea of gravity and then Kepler's idea of oval orbits.
Modern solar system. The solar system is well understood today. Astronomers have observed all 8 planets in the solar system, and space probes have visited each one of them. The modern model is based on Photosynthesis and the heliocentric model, and with Kepler's elliptical orbit. Use the exact origin of the solar system. All solar systems start with the information of the central star. The central star in the
I think there's still a lot of things to discover in this one, right?
Yeah.
Yeah.
Maybe tomorrow we should do that. Till tomorrow is Friday, isn't it? Okay, Friday.
Yeah,
Now I
Friday.
think it's good enough. It's good enough for now. Modern star system and things like that. It's for later, okay?
Okay.
It's for later then. Okay, that's the end of my videos. Please like, share this video with your friends, subscribe to my YouTube channel, and press on the bell button next to the subscribe button so you can get notified about my new uploads, okay? You can also press follow my Facebook, but please don't add me on Facebook as friends, okay? Cảm ơn các bạn đã theo dõi nha. Các bạn hãy nhấn vào like, chia sẻ video này bạn bè các bạn. Nhấn vào nút đăng ký kênh YouTube mình và nút cái chuông kế bên cạnh để đăng ký kênh á, để mà các bạn có thể được thông báo về những video mới nha. Các bạn cũng có thể nhấn vào nút theo dõi Facebook mình, nhưng nhớ đừng kết bạn Facebook mình nha. Thank you and see you. Bye.